Alright, so in this video, we have a few more MCQ here for you to practice. Need to pause, read, follow. I'm just going to run it fast. You have a hollow sphere that's rolling down. Coefficient of friction is given here. Angle is 35 degrees. And then the angular acceleration here is given as 4 rats per second square. And it wants us to calculate the radius of this particular hollow sphere. Alright, so here I'm just going to go ahead and set up my two torque function. The first torque function is the force that's generating the torque. In this particular case, if you use the pivot at the center of mass of the hollow sphere, it'll be the frictional force that causes the rotation of this particular hollow sphere down the ramp. Okay, and then the second function for torque is the moment inertia times angular acceleration. I need to apply both of these because, well, the coefficient of friction here is given, which suggests that you have friction, or the force of friction to play with. And then the angular acceleration is also given as 4 rats per second square. So alpha is given, and the angle here is given as well. Okay, so essentially you're given enough information to play with these two functions when you set them equal to each other. So I'm going to go ahead and do that. Here is the force times r equals I alpha. Well, what force is causing this particular object to rotate or generate this torque? That is the force of friction here. So I'm just going to call it Fs because the problem gives us mu s as 0.2, so I can apply that in my Fs function. So it'd be Fs times r, and then the moment of inertia for a hollow sphere rolling down the ramp, because its axis of rotation is through the center, is just 2/3 mr squared times the angular acceleration on the outside of the parentheses there. Alright, and from here really you just have to further expand in order to find the radius of the sphere. So I can see here on the left side I have an r. On the right side, I have an r squared, so I can go ahead and simplify this particular statement down by canceling out one of the r's on the left side with one of the r's on the right side. So essentially, you have an r term that you don't know here, so you can just go ahead and, like I said, just crack it out by just substituting in a bunch of stuff. Well, we know that Fs here, or the force of friction, is just coefficient of friction times the normal force on the ramp. And then on the right side, it's just 2/3 mr alpha. So once again, mu s is given. We don't know what f of n is, but hopefully incline knowledge is solid. According to my diagram here, the arrow that just came up acting on the sphere here, that is the weight of the sphere, which is drawn straight down the page. That's f of g. And then from there, you can break it down into f of gx and f of gy for an incline, because we take the surface incline to be our x-axis. And then perpendicular to that surface incline would be your y-axis. So here's f of gy, and then here's f of gx. And then this particular angle for the ramp is the same as this angle that's labeled here due to geometry. Okay, but essentially we need f of n. But if you look at this diagram and you've done inclined forces for this diagram, it's pretty straightforward. F of n is the force exerted by the surface onto the hollow sphere, and that's going to be perpendicular in the y-axis here. Okay, I'm just going to call that f of n. But the ball is just rolling down along the ramp, so its acceleration in the y direction is 0. So we can safely conclude that f of n is equal in magnitude to f of gy. Alright, so instead of f of n here, I'm just going to go ahead and substitute it out for f of gy. Now hopefully, like I said, you've been inclined. If not, watch my incline stuff. So fn here is just f of gy, and f of gy is simply the adjacent leg for this particular f of g. F of gy touches theta here, and that is the adjacent side. So I'm just going to go ahead and say f of gy is mg cosine theta. Mg comes from the fact that this is f of g. Once again, f of g is just mg, and it's the adjacent leg, so it's cosine theta. And then from here, you see that there's an m on the left side, there's an m on the right side. You can cancel that out. Keep in mind that you're trying to solve for r. So really, here you have a 2/3 coefficient. So to get rid of this 2/3, multiply both sides by the reciprocal of 2/3, which is 3/2. At the same time, divide both sides by the angular acceleration here, because this is the operation is to multiply. So to get rid of alpha here, you just divide. So I'm just going to go ahead and do that. So we're going to see the 3 on the bottom on the right side will be multiplied, which brings it up to the numerator on the left side. The 2 and the alpha are both being multiplied together, so you can just divide by, once again, 2 alpha together. That gives you r. So at this point, really, it's just a plug and chug in calculator. Coefficient of mu s here is given as 0.2, g is 9.8, and then the angle here is given as 35 degrees in the problem, and then alpha is given as 4 rats per second square. So if you just plug all this stuff in, you plug and chug, The answer comes out to be about 0.602 meters. So I'm going to go with choice B being the closest answer there. Okay, let's move on to the next one. So here you have a solid cylinder that's initially 3 meters up, and then it rolls down the ramp. By the time it gets to the bottom of the ramp, it has an angular speed of 2 rad per second as given in the problem. And this particular problem wants us to take g as 10 meters per second square. So instead of 9.8, the reason I'm sure it probably just ends up giving us one of these nice answers. Okay, so just keep that in mind as we practice here. All right, so here I know that the problem wants to find us wants us to find the radius, right? Well, if you think about it, you know the bridge function between linear speed and rotational speed, simply just multiplying by r. Well, I'm going to apply this because the angular speed is given as 2 rad 2 per second at the bottom. The question asks for r, which is really what I'm trying to figure out. I don't know what v is though. However, the problem gives you height. So essentially, if you're familiar with my other videos where I've derived the expressions for v in terms of h and the coefficient of moment of inertia, then that's where I'm going to use here. If not, again, please go back and watch the other videos if you need to, in order for you to understand this a little further. All right, so what I want to do is I'm actually going to square both sides here. Okay, so I'm just going to square v, square r, and then I'm just going to square omega. Here the diagram called the radius as capital R, so instead of lowercase r here, I'm just going to replace with capital R just for consistency with this diagram here. The reason I'm going to square this is I think it just makes the math a little easier to follow. Well, the v square function for some sort of rolling motion down an incline is given as 2gh divided by 1 plus c. And this, again, this proof has been done in my other videos. If you need to, go watch it. So here I want to square v because v squared is 2gh over 1 plus c. And then what you do on the left side, you gotta make sure you square the right side as well. So this just be r squared omega squared, which has carried down here. Keep in mind, we are trying to solve for r, okay? So therefore, I'm just gonna plug and chuck everything in. Well, g is 10, because this particular problem wants us to use 10. H is given as 3. The coefficient of a solid cylinder rotating around its axis at the center of mass here is just 1/2. That's where the 1/2 comes from. And then omega here is given as 2 rad 2 in the problem, right? So make sure you use parentheses. So instead of omega, I'm just going to plug in 2 rad 2, and then I'm just going to square that. So from here, I can simplify stuff a little bit. If you punch in your calculator, 2 rad 2 square is just 8. Or you can just think, distribute this exponent. 2 squared is 4, and then rad 2 squared is just 2, and then 4 times 2 is just 8. That's where that 8 comes from. And on the top, 2 times 10 times 3, that's just 60. And on the bottom, 1 plus 1/2 is 3/2, or 1.5. Right? If you have a dollar, you plus 1/2, which is 1.5. But 1.5 really in fraction is 3 over 2, or you can find common denominator, however you want to do. But ultimately, just make sure you do your algebra correctly. So here you have 60 divided by a fraction. So really, you have to multiply by its reciprocal. So instead of saying 60 divided by 3/2, I'm just going to say 2 times 60 divided by 3. As you can see at this point, you're trying to solve for r. You have r squared times 8. So the next step you need to do is just get rid of the 8 by dividing both sides by 8. So I'm just going to move the 8 from the top right to the bottom left and combine that with the 3 there. So here you see that you have 2 times 60, which is 120, and then this is 24, which is equal to r squared. So if you punch in 20 divided by 24, you'll get 5. But this is r squared, right? You're not done yet. So don't jump the gun and pick a here. This is r squared. So how do you find r? Well, just square root both sides. So therefore, r is the square root of 5. So that would leave you with d. Okay, so this is one way to do it if you know your expression for v squared is 2gh divided by 1 plus c. So I highlight that because that's an essential skill. So if you don't have it, brush up on it. Now, you can do this problem in a little, ultimately it's all pretty much the same, except I think it's just your starting point that you can maybe utilize a little better. So for this one, I'm just going to go ahead and start with conservation energy. Initially, the solid cylinder here is at the top of the ramp, so it has to have a PE due to gravity initially, and then it starts to roll down. At the bottom, it has to have 2 forms of KE because it's moving linearly and it's also rolling. So here in my work, I just have mgh equals 1/2 mv at the bottom, square plus 1/2 I omega square. Again, this is the same problem. Just keep in mind, we're solving for radius here, right? So here in my work, I don't have any R here, but what I can do is just go ahead and substitute stuff out. So MGH just gets carried down. The 1/2 M just gets carried down here, but V by definition is just R omega. So in parentheses I have R omega. And then I, the moment of inertia for this particular solid cylinder is 1/2 mr squared. The omega squared just gets carried down. So at this time, I'm just going to go ahead and cancel m out just because it appears on both sides and it's in every term. And then I'm just going to clean up a little bit. So the left side really just leaves us with GH. On the right side though, the exponent for this particular parentheses must be distributed to the r and the omega, hence the 1/2 r squared omega squared. And then here 1/2 times 1/2 is 1/4. And then r squared omega squared just gets multiplied and gets carried down. Alright, so at this point, if you want, you can just use common sense, or it's up to you. Like I like to think like 1/2 is 50 cents, and then 1/4 is a quarter. Well, 50 cents plus a quarter is 75 cents, which is 3/4 of a dollar. Or if you want, you can just do basic math and find common denominator. As you can see here, this is the 1/2 is 1/4. Well, 1/2 and 1/4 don't have the same denominator, so to get the same denominator, you just multiply the first term here by 2 on both top and bottoms. Hence, I highlighted the 2 and 2 here. So it'll be 2 times 1, which is 2, and then 2 times 2, which is 4. So if you think about it, this is r squared omega squared. The second term here also has r squared omega squared. So 2 times 1 is 2. 2 plus 1 in the numerator is 3. And then the denominator here is 4. All right, 2 times 2 is 4. This is also a 4. So really we get 3/4 of r squared omega squared, which again, as I said earlier, if you just kick in common sense a little bit, 1/2 is 50 cents, a quarter is 75 cents, and 75 cents is expressed as 3/4 because it's 3/4 of a dollar. All right, here I'm just going to isolate for r squared because ultimately that's what we're asked to find. So to solve for r squared, I'm going to multiply both sides by 4, divide both sides by 3, and then also divide both sides by omega squared. So it'll do a little switcheroo. Okay, so the 4 on the bottom right here goes up to the top left. The 3 being in the numerator goes down to the bottom left, and then omega squared being in the numerator as well goes in the bottom left as well. So here at this point, you just plug and chug. 4, G is 10, H is 3, and then once again, omega is given to us as 2/2. Make sure you use parentheses there. If you square that, once again, 2/2 squared is just 8. So I'm just going to keep carrying my work down here. Here, I'm just going to cancel out the 3, by the way. It's up to you. I mean, you can punch all this in your calculator, just recognize that there's a 3 on top, there's 3 on the bottom. That can just cancel out. So essentially, you have 4 times 10, which is 40. Well, 40 divided by 8, which is 5, right? But keep in mind, once again, that's r squared. Well, to find r, you just square root both sides, so therefore r is just square root of 5, which again leaves us with the same answer as the previous strategy. It all depends on how you want to solve these problems and how you see them. All right. Last but not least, in this particular video, here you have a uniform solid disk. It's being dropped essentially at this particular position in the the solid color coded here, or copper they call it. All right, and it wants us to find what is the speed of the lowest point on the disk in the dash position. So to help you visualize this, it says the lowest point. So the lowest point once this particular disk swings down is at the bottom there, and it's going to be moving in this particular direction. So I'm just going to call that V. So it wants us to find that V. All right. So here right away I recognize this is conservation energy because essentially the center of mass of this particular solid disk, it's at a certain position, and then it's going to drop. Well, you have PE, that's going to be converted to KE. So I'm just going to go ahead and set MEI equals MEF. And then, well, what's my initial energy? My initial energy is just going to be energy due to gravity, because again, you have to be able to visualize that this particular disk was raised to this horizontal position and then released. So that particular work got stored in the form of PE, and then that PE will be converted to KE. Okay. On the right side of this particular ME though, I have only KE rod. Keep in mind, it's fixed at the very edge, so it's swinging, but it's really not like moving from A to B. Okay, like it's fixed to a pivot. All right, so there's no KE linear. There's only KE rod because the disc is just rotating back and forth, or it's swing back and forth. All right. On the left side, I'm just going to break up PE equals MGH. I highlight the H here, and this is important. I think this is where a lot of folks might goof just because you won't measure things correctly. KE rotational is just 1/2 I omega squared. I highlight this I2 because, as you can see here, the pivot is not at the center of this particular disk, right? It's at the very edge. So you have to pay attention to all these conditions given as you practice these problems. Otherwise, you're going to goof on the physics part, and the algebra is going to just mess you over. All right. Here I've drawn 2 lines for you. I like to do this once again just so I can pinpoint, well, where did it start from, right? Here's the pivot, and then the center of mass, as you can see here, as it gets dropped, it's going to kind of swing and trace out like this circular arc. So at the lowest point, the center of mass, again, is at the center of mass. So I like to do this because then I know how far down that particular center of mass has dropped. So the center of mass is located here. By the time it's in this vertical position, if you can kind of visualize it, trace out that arc. The center of mass here is in the center, and that is a distance of r. Okay. Now, as I said earlier, I highlight this I because often folks might just go, well, it's a uniform solid disk, so they'll use 1/2, but that's not the case. You can only use 1/2 if it rotates at the center as its pivot, right? But here the pivot is at the very, very edge, so you have to recognize that you have to use the parallax theorem here in order to find the new moment of inertia for this particular system. So here in my work, I have I nu is equal to I center of mass plus md squared, d being the distance shifted from its axis of rotation originally, or center of mass here. All right, other than that, I'm just going to go ahead, ICM for the solid distance is 1/2 mr squared, and then the distance shifted is just r because it went from the center to the edge, which is the distance of r. And here you have 1/2 plus 1, and that's 1.5, or you can express as 3/2. It is entirely up to you, right? You can multiply the right term here by 2/2 to find common denominator, and then 1 plus 2 is 3, and then the common denominator is 2, or you can use common sense. This is 50 cents, that's $1, that's $1.50, and $1.50 in fraction is just 3/2. All right, so I nu here is 3/2 mr squared, so I'm just going to go ahead and substitute stuff in. So I made a note for you here to make sure you use the reference point. It's a common error for folks to put in HS2R because they're always thinking the lowest point. But when a shape of this type of problem moves, you have to reference center of mass. How far did the center of mass displace, whether it's vertically upward or downward? Okay, so here in my work, mgh equals 1/2 I omega squared. I'm just going to plug in true statement. H is only going to be R, not 2R, right? Don't just measure from top to bottom. You have to measure from pivot here in this particular problem to center of mass, which is just a distance of R. Well, I here is not 1/2 mr squared. It's actually 3/2 mr squared because you have to use the parallax theorem to adjust the fact that it's being swung at the very, very edge of the disk. All right, so if you understand those essential concepts, the rest is just kind of basic. Here, there's an m on the left side, m on the right side. I'm going to cancel that out. And then I'm just going to simplify my work. 1 times 3 is just 3. 2 times 2 is 4. And then from here, we can just clean up R a little bit. Oh, I'm not sure when this animation is going to come up. My bad. There's an R on the left side here. And then there's an R square on the right side here. So one of these R on the left side is going to cancel with this R, or one of the R square term here on the right side. So in case you didn't keep up there, hence it's just 3/4 times R because one of the R's cancels out. All right. So ultimately, once again, we're asked to find the speed at the lowest point. So I'm going to go ahead and isolate for omega here because once I know omega, I can find V linear. So in order to get omega squared by itself, I'm just going to multiply both sides by the reciprocal of 4/3 and then divided by R. So the 4 on the bottom right got moved up to the top left, and then the 3 and the R on the top right will be moved to the bottom left. Okay, but here we have omega squared, so therefore to find omega, just take the square root of the term here, which is 4g/3r. Well, what do you do with this, right? Well, once you know omega, you can find v, because the function for v is r omega. So here, well, what is r, right? R here is 2r. Well, why is it 2r? Because the question is asking us how fast is the speed of the lowest point from the pivot to the lowest point of the outer edge of the disk. It's the distance of 2r. So it's important that you apply these definitions correctly. And then omega here I just solved already, which is just a square root of 4g/3r. Other than that, at this point, really you just have to recognize. I think this is usually where these answer choices can be a little tricky if you don't recognize. Well, if you look at it, underneath the radical sign, you have a 4. Well, what's the square root of 4? 2. So 2 times 2, if you factor out the 2 there, if you took the square root of 4, that'll just be 2 outside the radical sign. So 2 times 2 is going to give you a 4, right? But here you have an R on the outside of the radical and also an R in the inside of the radical. So what I'm going to do is I'm actually going to undo this R, So I want to call this an r squared. I want to put it back inside the radical, which is true because the square root of r squared is just r. So you have to kind of see when you simplify it and when you undo it. So this is where the 4 comes from. There's already a 2 in the front. The square root of 4 is 2, so 2 times 2 is 4. Why is there an r squared inside? Because I just undid this square root. So these are tricks once again you just have to see. So in order to you have an r in the front, you must have had the same term square inside the radical. So it's r squared. But now you have an r squared on top, you have an r on the bottom. So it's going to cancel out a little bit here, okay? So essentially you're left with just a numerator of rg divided by 3. Alright, so if you look at that, if you clean up, it'd be 4 times the radical, or the square root of g times r divided by 3, and that is going to match with answer choice, let's see, A. You have a 4 on the outside. Why in my work I have g times r, they have it as r times g over 3, which is the same thing. Okay, that's that. All right, I hope that helps. Stay nerdy, don't be black.